Hi, I thought what we'd look at today is how we take the vectors beyond the GCSE work, which overlaps greatly with the AS single maths, and how we take it forward to the AS further maths, which is chapter 9 in the further maths book. It's the further maths pure book, not the mechanics book. First thing they do is they introduce the idea of three-dimensional space. So we have the x-axis, we have the y-axis, we have the z-axis. We could describe, let's say a point had an x-coordinate of 2, a y-coordinate of 3, and a z-coordinate of 1. Then that vector in column vector form would be 2 across, 3 along, 1 up. In the new format we're looking at, it'd be 2i. Unit vector in the x direction is I, 3j plus 1k. So 3 dimensions, x, y, z axis, I, j, k components, or a column vector with 3 parts. Hopefully you're thinking an obvious extension to what we're doing in 2 dimensions. The size, the magnitude of that, nicely is a direct extension of the Pythagoras we've done. It's the square root again of 2 squared, 3 squared, and 1 squared. The length of any vector is the sum of the square of the components square rooted. So in that case, 4, 9, 10, root 10, whatever that is. Right. The next bit of the X chapter, so almost the very first bit, is the idea of a vector equation of a line. If we've got a line like that with a point A on it, so let's say we've got, if that's the origin, we've got a point A whose position vector is vector A, and let's say the line is in parallel to this vector. So position vector of a point of the line, direction vector giving direction of the line. The vector equation will be R is A plus lambda B. What on earth does that mean? R is the the position vector of a general point on the line. R is the vector that takes you from the origin to any point on the line, general point R. To get to that point, we could go to A and then along the line. Going along the line will be some multiple of B. So getting to the line, travelling along the line, gives us the equation of any line. So, for example, the equation of the line through equation of line through 215 and parallel to 312 would be R equals position vector of a point on the line and a multiple of that direction vector. Now, if you're thinking there's an infinite number of points we could use for this bit, you're completely correct. So let's, for example, say if it goes through that point and it's parallel to that, another point on the line would be 215 with one of those added. So 215 with that added, so 5, 2, 7. That's another point on the line. I'm going to use a different scalar as a multiplier, but that and that are both equations of the same line in vector form. And there's some nice work in the book talking about the three-dimensional work and the two-dimensional work. which is enough to get you through 9a. In fact, no, I'll do one more example because I can do that. So I'll get rid of that. We'll come back to vector equation of a line in a second. Good question would be, at GCSE, you were sometimes asked for find the vector equation of the line that passes through, let's have 2, 1, 5 and -3, 3, 8, for example. Can we find the vector equation of a line that goes through x, y, z, 2, 1, 5 and -3, 3, 8? Well then, can you already see a limitation of these diagrams? That doesn't really help at all, does it? But that doesn't matter, okay? We want the vector equation of that line. So all we do is we need a point on the line, which could be either, and the direction of the line. The direction of the line, we could use the vector that takes us from that point to that point. So B could be, the direction of the line could be expressed as how we go from there to there. So the position vector of one point, take the position vector of the other point. So 5, -2, -3. And then we've got a choice for the equation of a line could be that point, 2, 1, 5, and a multiple of the direction. And an equally good equation would be -3, 3, 8, and a multiple of the direction. And if you're thinking now, well, hang on, what about 2, 1, 5 and the opposite direction? Change the signs. They'll be equally good. Lambda, omega, I don't know, that's running out of ideas. They're all vector equations of the same line. Vector equation of a line is a point on the line and a movement along it. Now, if you want a glimpse into the future, we are going to talk about, when we do some of the more mechanics, we're going to talk about the position of something being its starting point and a multiple of the velocity, if the velocity is constant. And that's exactly the same equation. Right. The other key bit in the first two sections of this chapter is how we go from a vector equation to a Cartesian equation of a line. Okay, Cartesian equation, y equals mx plus c, is an example of a Cartesian equation in 2 dimensions. It was relatively easy, but there are complications with getting a 3-dimensional Cartesian equation, but there's a straightforward way of getting them. Let's pick, I'm going to pick the one I've just done. Let's say we've got this Cartesian equation, this vector equation, 2, 1, 5 plus lambda 5 -2 -3. I could write that, I could combine the I components together, 2 and 5 lambda. 1 take 2 lambda is combining the j's, combine the k's, we get 5 take 3 lambda. Or I could consider that to be the x, y and z coordinates of the points on the line, in the same way we had x and y here. This is the Cartesian. If I can write something like that with the x, y and z relating to each other. That's the Cartesian form. So how do we go about it? Well, we take 2 plus 5 lambda equals x, and I write that as lambda equals x take 2 over 5. I take 1 minus 2 lambda equals y, and I rewrite that as, I'll put the lambda on that side, so lambda is 1 take y over 2. And you might have guessed it now, I now take the z, 5 take 3 lambda equals z, and I get lambda equals 5 take z over 3. I've got lambda as the subject, lambda as the subject, lambda as the subject. So they're all equal. I can put that equal to that equal to that. The Cartesian equation for this line is that equal to that equal to that. X, y and z related to each other. Now, 2 dimensions, one thing equal to another. 3 dimensions, 1, 2, 3 bits equal. Now there are some special cases, but before we do that, can I point out another way of writing exactly the same thing would be, so I could write x take 2 over 5. I could write y take 1 over minus 2. I could write z take 5 over minus 3. Why have I bothered to write it like that? Because the direction vector appears here, and a point on the line appears here, but with the signs changed. So it is quite useful to know if we've got r equals a plus lambda b, and if we say a is a1, a2, a3, if we say b is b1, b2, b3, the Cartesian form is always x take a1 over b1 equals y take a2 over b2, z take a3 over b3. And that's a neat shortcut to work from one to the other. Now, that would be a good place to get to at the end of tomorrow if you were then to read chapter 9, sections 1 and section 2, sections 1 and 2, and try the questions in 9a and 9b. Tell you what, why don't upload work to Edmodo so I can see you trying it, but also any questions. Okay, good luck with that.